I forgot to record on Monday, but we didn't really cover anything that wasn't in there. So I'm going to record today and I'll show you where those get posted. So on our Canvas page, which now has a cute little chemistry logo to help you identify it, on our Canvas page, if you click on modules, and I know it might look different in the app, but somehow you can get to modules. If you click on modules, then you can download the notes from each chapter, or the course information has the syllabus notes. And then I have links to the current assignments, links to future assignments on Alex. And then each chapter has its own module. So chapter 1, there's what I call blank notes. We're going to write on those today so that you don't have to write down everything that's on the slide. Some of it's already there, but you can write down the things that I think are most important that I will write down with you. So we're going to go over chapter 1 today, and then I will put the recording from today in there as well on this chapter 1 module. Any questions about anything on Canvas, anything on Alex, iClicker? Okay. If I don't see you have a hand up, just yell. Okay, cool. Guess that's no questions. So once again, if you came in the last couple minutes, this QR code up here is to get into our course GroupMe, which is just like a chat feature for us. So you can, get questions answered a little faster in there than on email. All right, and then I told you that I like to show pet pictures. So this is a baby cow picture. These baby cows are now very large cows. So this one's about 1.5 years old. But they were cute when they were little. They're still kind of cute, but they're always cuter when they're little. So the number 9, her name is Azumi, and her brother, his name was Vesper, which if you remember anything from high school chemistry, you might remember Vesper theory. If not, we're going to get to it in chapter 10. So, okay. And then our announcements. Chem 119 labs start this week. You'll do everything when you're in lab. If you miss lab, make sure you go over to the ILSQ to sign up for a makeup lab. You can come ask me about that at the end if you have questions about that. If you have any problems with Alex, let me know about that too. If you weren't able to join the iClicker last time, you might need to use this link, this website, to join today. But if you were able to join last time, it should be easy to join this time. And then reminder, we have a participation assignment on Canvas, which is the personal introduction assignment. If you filled out the little discussion post, that is for you guys to get to know each other. But the personal introduction assignment is for me to get to know you. And you can put more, I don't know, more personal stuff in there than you might put on the discussion. But that's for me to get to know you. I look back at those if you ask me for a recommendation letter. So put some stuff in there that I will remember who you are. And then also due Monday night are the 2 homeworks, chapter 1 and chapter 2, part 1 on Alex. And then this is a little bit of ways, but I wanted to make sure you guys saw it on the syllabus or saw it on the announcements. We do have a mini exam in class on September 11th. So that is not next Friday, but the following Friday. We'll have that mini exam in class. It's about 30 minutes, so not as long as a real exam, but it's good practice for where you find your seat, because you will have assigned seats. It's good practice for passing out the exams and collecting the exams. So the mini exam is only worth 2% of your grade, so not a big deal, but it will help things run smoother when we get to exam 1. Any questions about any of these things? So normally from now on, I will probably have the announcements on the slide when I get here, and I won't really talk through them too much. But just want to make sure we're all on the same page since we're just getting started. Okay, so let me move this. So the chemistry learning lab, that is going to open on Monday. This is free peer tutoring. So you don't have to go if you need help. You can go just if you want a good place to study, a good place to work on your homework. You can go with your friends. You don't have to go for 3 whole hours, obviously. But just drop in there, and we do have worksheets that you can work on. So I do suggest picking up the worksheets while you're there, not just working on homework. If you scan that QR code that's in the top corner, is it working for people? Were you able to scan it? I don't know if it's too small, but if you scan that QR code, we are starting something new this year, which is the virtual chemistry learning lab, because I know 3 hours, 4 days a week is not the most accessible. So we're starting a virtual chemistry learning lab, and if you want access to that, you'll fill out a little bit of your information, and I will sign you up. All right, any questions about that? Any questions about the learning lab? Okay, the virtual learning lab will also start probably next week, however long it takes me to sign everybody up. Okay, so I went over this or skipped over it last time, but why I make you do assignments, there's a why. It's not just because I'm mean. I make you guys do assignments in class. I make you do problem solving with iClicker problems. They help you with problem solving, determining the level of understanding of the material, communicating with your neighbors. So chemistry is definitely, during a test, it's a solo activity, but any other time, it should be a team activity. I think it really helps to work with other people and learn from them and teach them. I think the best way to learn is to teach others. So I've learned a lot more about chemistry since teaching it than I thought I would. And then outside of class, you will practice your skill building and higher level, like answering higher level questions, critical thinking with your homework, learning about proactivity, how to study early, not just the night before the test. I will release the mock exams about a week before each test. There won't be one for the mini exam, but for all the other exams, there'll be a mock exam, which will help you with test taking strategies and time management in exams. And then again, outside of class, you can network and communicate with your classmates. I think forming study groups is really helpful. And I do have a study plan assignment in a couple weeks that we will go over, and that will help you form study groups if you are, a little shy and don't want to necessarily talk to your classmates right now. I will help you with that. So I think I talked about this last time. A lot of students tell me that they didn't really have to study in high school. So I'm going to help you learn how to study. I'm not just going to throw you in the deep end. So some suggestions for studying is looking at the textbook before the lecture. And I showed you guys how to find the ebook last time, but if you forgot, come let me know. And coming to lecture and taking some detailed notes. So it has been shown that taking notes by hand is helpful, whether that's on a notebook or on a tablet. I've heard that that is a little more helpful than typing, but do what you got to do. Just make sure you're not just kind of staring at me. You are taking notes, being active with your learning, active with your studying as well, organizing the material in a way that makes sense to you. Whenever you do a difficult problem, I suggest going back over it and kind of explaining every step of what you did. That will help you prepare for another difficult problem like that. Working the problems, practice, practice, practice. When you practice difficult problems, I would suggest trying them the way they're written, and then maybe plugging in your answer and working backwards to try and get one of the other variables that you started with. Writing down your work. We're going to talk about units today, canceling out units. That's very important. That's why I want you to write down your work, not just do everything in the calculator. And then try to do your homework without looking at your notes. Really test yourself so that you are prepared for when you get a test and you don't have your notes. Coming to my drop-in hours with questions, studying more than just the night before the exam, all that good stuff. And these suggestions are all also posted in those syllabus notes from the course information module. And then this little infographic is strategies for effective learning. So different strategies are elaborating, really going into detail of what you mean when you answer a problem. Retrieval practice, which is basically testing yourself. Spaced practice, which is testing yourself not just the night before the exam, but the night after you learn the material, 2 nights later, 3 nights later. Um, Dual coding is if you are kind of a visual learner, you can draw pictures or flow charts to help you match the concept to a picture. And then making sure you write some really good examples, analogies that make sense to you. My analogies hopefully will make sense to you, but maybe not. So make sure you can try and think of some of your own if you need to. And then interleaving, that is what is called drilling on one concept for a little bit and then going to something else. So it doesn't even have to be chemistry. Like you can study chemistry for an hour and then go, or half an hour, and then go do something else, bio or whatever for another half an hour and then come back. So studying all at once the night before an exam, not effective. Studying some things and coming back to them later, more effective. Okay. And then just an overview again of why we're learning chemistry. So I know we've got a big mix of majors in here. I probably won't be able to name them all, but we've got like bio, we've got BIMS, we've got probably some neuroscience, we've got animal science, we've got some engineers, got food science, I think I saw in the discussion board. Just a whole bunch of different majors. If I didn't say yours, kinesiology, nutrition. If I didn't say yours, it's because there's so many. And I forgot, I don't know. But there's lots of things. We call chemistry the central science. My turn up volume is right over that subtitle. But we call chemistry the central science because it applies to all of those different topics. It applies to medicine, it applies to engineering, it applies to earth sciences, ag. So that's why we're learning chemistry. So now we're gonna jump in. So chapter one is about kind of the intro, obviously, to chemistry. So we are gonna identify common units, which you probably are already familiar with units and prefixes from the prep module, hopefully. We're going to talk about significant figures, which was also in the prep module, and calculations. And then we're going to talk about something called dimensional analysis, which I don't know if they called it that in the prep module, but you did some of that unit conversion in there as well. We're also going to talk about pictures. We're going to look at some pictures and talk about how you can identify a solid from a liquid and a gas based on the molecular picture, not obviously we know what solids, liquids, and gases look like on the macro scale, but we're going to look at them on the molecular scale too. And physical and chemical changes. We saw a little bit of that with our demo last time. That was physical change. We'll talk about what chemical changes are too. All right. So chemistry is all about trying to explain macro scale changes based on molecular interactions. So chemists observe systems and try to understand why or how they are happening based on the molecules, not based on what they see. So boiling water, for example, we've probably all boiled a pot of water. Maybe you're making pasta, maybe you're making tea. That'd be a kettle maybe, but whatever. Boiling water looks different on the molecular scale than on the macro scale. So boiling water on the molecular scale, instead, when we think of a liquid, this is going to be a spoiler later in the chapter, but when we think of a liquid, it is a collection of molecules that are pretty close together. And they're kind of disordered. So that's what we see in the bottom picture is a liquid. So liquid water, those molecules are kind of all jumbled up, but they're close together. A gas, gaseous water or water vapor, that is where the molecules are more spread apart. And that's why we can, walk through air so easily, because the gas molecules are spread apart. They just kind of move when we walk through them. Liquid water, you can move through that too, but it's a little harder, right? So those are kind of the differences. We're going to talk about the phase properties, what liquid water and gaseous water look like on the molecular scale, and how that affects their properties, like how you can move through them. So we want to talk about what those scales are. The macro scale is viewable with the naked eye. So it could be something really big, like a skyscraper, or just like something that's about a mile in the distance, maybe. Or it could be something smaller. You can probably identify or distinguish between length scales down to maybe a millimeter, which is the width of a CD. So it's how far you can see in the distance versus the smallest you can see. And I like to write on the slides, not necessarily, you don't have to write exactly what I write, but just so that if you are taking notes on what I'm saying, you have time to write them down. So then we have a kind of intermediate scale. This is the micro scale, and it's viewable with a microscope. You've probably used a microscope in like a biology class before. So you use microscopes to look at plant cells or bacteria or pollen grains. Use a microscope to look at things that are between about what we call 1 micrometer and less than 1 millimeter. So 1 micrometer, just to put that in scale for you guys, the width of a human hair is about 100 micrometers. We also call that microns sometimes. It's the little Greek mu, and then m for meters. So bacteria are 100 times smaller than that, but we can still see them with a microscope. And then the atomic scale, not really viewable, for most common people, but technically we can view things down to almost individual atoms using electron microscopes, or what we call atomic force microscopes. So SEM is scanning electron microscope, TEM is transmission electron microscope. I'm not too, it'll take a while to go through the difference between those. And then atomic force microscope, that's a little bit different. That one is more about measuring the heights when you're kind of drilling into something with a needle, basically measuring how far down it goes and making a picture based on that. So atomic scale. Fun fact, the atomic scale gets a special unit. We won't use this too often, but it's basically made just for the width of atoms. It's called the angstrom. It's not one that fits in nice with meters, picometers, femtometers. We call it an angstrom. Don't have to worry about it, but just a fun fact. And then you can see kind of the scales in that graphic there, the distance from the Earth to the sun. We can't really fathom that distance ourselves, but technically we can see it with our eyes, sort of. And all the way down to that small atom, a helium atom is the smallest one, and that's on the order of 100 picometers or 50 picometers, somewhere in there. So it's helpful to talk about the scales that we're looking at. So the scale of chemistry using a microscope, like I said, you can look at a human hair and you can see the width of a human hair. Regular hair, that's the picture on the left at the top. Hair under a microscope, that's the picture at the right on the top. And you can see the scale with this little scale bar on the picture is 10 micrometers. So it's about 100 micrometers across. And then if you get a stronger microscope, a scanning electron microscope, you can look at red blood cells. That's what you see in the bottom left. So the red blood cells have that cute little hollow in the middle for the oxygen to carry it along in your bloodstream. And then the picture on the bottom right is, those are individual, well, it's an individual molecule. The atoms themselves are like the corners of that picture. So I wouldn't say that we're technically viewing individual atoms there. We're definitely viewing individual molecules though, which is kind of cool. So that molecule is called pentacene. It's basically 5 carbon rings next to each other, which is kind of fun. So you can see what one looks like, and that's the 5 angstroms is the scale on that picture. Or you can see what 6 of those molecules look like. That's the 20 angstroms. They're about 20 angstroms across, it looks like. Okay, so when we talk about really small things, sorry, I'm talking a lot today. You'll get to do fun stuff soon. When we talk about really small things like water molecules, that means if they're really small, you can fit a lot of them into a different space. So if you're trying to look at a glass of water, for example, a bunch of water molecules fit in there. So you might not think about it when you're drinking water, but a glass of water, a typical glass of water, can hold 7.9 times 10 to the 24 water molecules. So that's a lot of water molecules. And if you want to think about it, I would think about how many Skittles, if you try to put Skittles in a glass of water, how many Skittles you can fit in there. It's not going to be as much. You could probably actually count the number of Skittles in a glass of water. And that's because they're bigger. So those things are kind of inversely related, size and the number of things that fit in a glass or a container. So as the size gets bigger, comparing a Skittle to an atom, fewer of them can fit. And when we talk about very large or very small numbers, we're talking about scientific notation. So scientific notation is that times 10 to the whatever. So the number that comes before it, 7.9 in this case, 7.9 times 10 to the 24. 7.9, that number is always between 1 and 10, or 1 and 9.999. And then the power of 10, the 24 in this case, tells us basically the magnitude of that number, how many zeros it's got after it. So let's take a look at some scientific notation. This infographic tells you about scientific notation. Big things to take away from here is that when you're writing a big number in scientific notation, it's going to have a positive exponent. When you're writing a small number in scientific notation, it's going to have a negative exponent. So the positive exponent is when you move the decimal place to the left to make your number, to change your number from 5,630,000 to 5.63. But then we have the exponent part as the number of places that that decimal moved. It moved 6 places to the left. So that times 10 to the 6 is going to show us that the number 5.63 is a really big number, actually. 5.63 times 10 to the 6. When it's negative, when it's a small number, we move the decimal place to the right. And technically, you can write something like 584 times 10 to the 7th, but it's not correct scientific notation. When you're asked for scientific notation, especially on ALEX, it's always going to want that number part to be between 1 and 10. All right, so now we're going to practice. So what is that, 8 trillion? So 843,000,000,000,000,000 in scientific notation. So what is that number in scientific notation? And you guys are going to enter your answer as in the clicker thing. So feel free to write it down. I think that's not a bad idea. What is that number in scientific notation? I think it is 8 trillion. 8 trillion, 430 billion in scientific notation. Feel free to talk to your neighbors, check your answer. Make sure you didn't miscount your zeros. There are 10 zeros. So it's 8, 4, 3, and 10 zeros. I know it's hard to count. You lose track of the zeros. All right, I'll give you guys another 50 seconds. So I'll cut you off at 2 minutes. Again, this is just for practice this week, so don't be worried if you don't get your answer in. All right, 10 seconds. Get those answers in. Oh, we're only missing like 10 people. That's awesome. All right, 5, 4, 3, 2, 1. Blast off. All right, 449. And how'd we do? Okay, good. So it is A. I'm going to mark it as correct. So you will be able to see if you missed it, you'll be able to see that on Canvas. But like I said, I'm going to get rid of the points this week. So do not sweat about that at all. Nobody picked D, which is good because it's a big number. We want it to be positive exponent. And it's just about how many places we move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I know it's a lot of zeros, so you might have just wrote it down wrong. Totally fine. All right. So let's keep going. So some tips for you guys for entering scientific notation in your calculator. So I know that calculators have this times 10 to the whatever button, but I'm telling you right now, do not use that button. There's another button on your calculator that has an EE symbol or an EXP, and it might be a button you can just press, or it might be one you have to do second to get to the EE or second to get to the EXP. Use that button instead, because if you use the times 10 to the something button, then you are going to risk your order of operations and getting it wrong, because if you don't use parentheses correctly, it could get mixed up. If you use the EE or EXP button, you don't have to worry about the parentheses. So if you wanted to enter the number 1.24 times 10 to the negative 26, you would just type in 1.24, find that EE or EXP button and press it, or second it if you need to, and then just type the number 26. Sorry. And then you'll need the negative sign. You can do the negative sign before or after, but make sure you use the plus minus sign, not the subtraction key. The subtraction key will give you an error. It's going to be a plus minus sign to make your number negative. So in your calculator, it will look like 1.24 e negative 26. That is what you want it to look like. And that will have the right number for you for your calculations going forward. And I can go over that with any of you, help you find those keys on your calculator. Just let me know. Okay, so here are our prefixes, the metric prefixes, and there's like 4 that I would like you to memorize. So there's a bunch on here, but the 4 that I would like you to memorize are kilo, centi, milli, and nano. So kilo would be like a kilometer. So if you run a 5K, that's what the K stands for. Kilo is 1 times 10 to the third, or 1,000 meters. And the way that you use this table, these these prefixes is so that you never get mixed up. What I suggest when you're doing unit conversions is you always keep the 1 with the prefix. So 1 km, 1 cm. If you're talking about milliliters, that's a volume instead, 1 ml. Always keep the 1 with that prefix, and then the power of 10 with the base unit. So 1 kilometer is 1 times 10 to the third meters. 1 centimeter is 1 times 10 to the negative 2 meters. 1 milliliter is 1 times 10 to the negative 3 liters. So that way you'll never get mixed up if it's always 1 with the prefix. And then the power of 10 with the base unit. You can talk about seconds too, nanoseconds. So that would be 1 times 10 to the negative 9 seconds. Any questions about these prefixes? So kilo, centi, milli, and nano are the ones I would like you to memorize. All the other ones I'll give you if you need them. You might have to look them up on your homework, but on a test, I'll give them to you if you need them. Okay. So I think you guys did plenty of practice with sig figs. Plenty of practice with sig figs in the prep module. You're going to do lots of practice with sig figs in the lab, but I just have 2 slides in here that are like tips for sig figs. So biggest tip, don't round anything until the end. So if you're writing down your steps on paper, write down all those extra digits, like at least 3 extra digits until the end. Don't round anything until the end. Addition and subtraction with sig figs, your answer keeps the lowest number of decimal places. Multiplication and division, your answer keeps the lowest number of significant digits or significant figures. So a couple examples here. So addition and subtraction, if you had 2.34 plus 5.2, for example, just addition. So addition or subtraction, the rule is decimal places. So 2.34 has 2 decimal places, but 5.2 only has 1 decimal place. So our answer should only have 1 decimal place. So in your calculator, you would get 7.54. But that 4 doesn't count. So we would have to round. If it's a 4, do you round up or down? Down. So this would actually be 7.5 because it's based on our lowest number of decimal places. So with sig figs, you get rid of the 4. You round down. If it was 5 or higher, 5 through 9, you round up. So what are significant figures? Any non-zero number is significant. 111 has 3 sig figs, 111. They're all significant. Zeros after a decimal point and after a non-zero number are significant. So 0.024, those zeros are not after a significant number. So that means that those zeros are not significant, even though one of them is after a decimal point. So that one only has 2 sig figs, the 2 and the 4. But 0.02400, those zeros are after the decimal point and after a non-zero number. So those zeros after the 2, 4 count. So 0.02400 has 4 sig figs. Those zeros are significant. And then zeros between significant digits are also significant. So any zeros that you find between significant figures, those are also significant. So 100.0, the 1 is significant, and the 0 after the decimal point and after the non-zero number is significant. So the zeros in between are 2. That's 4 sig figs, 100.0. Any questions about those? And you might be wondering, why do I care? Why do you care about sig figs? Sig figs are important for measurements. So they tell you what part of your measurement is useful, what part is important. So they are useful for measurements. You'll see it a lot more in the lab than in the lecture. but I try to always have the right sig figs in lecture too. There's something up here about averages and standard deviations. You'll probably see that in the lab. They'll talk about that more there. Counts and exact numbers. So counts and exact numbers, if you're counting something like 12 eggs, that isn't 2 sig figs, it's unlimited sig figs. If you're talking about the number of inches in a foot, there's 12 inches in 1 foot. Those don't have 1 or 2 sig figs. Those are unlimited sig figs because there's exactly 12 inches in a foot. Exact numbers. And then you'll see the bottom ones in lab. Digital scales, all the digits are significant. And glassware, we determine the smallest markings. So in this picture, it's got 50 to 60, 60 to 70 with 10 tick marks in between. Because there's 10 tick marks in between, that's the ones place, 61, 62. You can clearly identify where those markings are. You round to the next digit. So this picture I would call 67.8. You look to where you can identify it for sure, which is, in my opinion, between this marking and this marking, because I'm looking for the bottom of that meniscus. So that's between 67 and 68, closer to 68. So I call it 67.8. You'll get lots of practice with that in the lab, though. Any questions about any of that? Okay. So we're going to talk a little bit about density too. Does anyone know what the formula is for density? Mass over volume, yeah. So it's an object's density is its mass divided by its volume. So density, in physics class, you might call it a rho, but I'm going to call it a D, D for density, is mass, which is an M, a variable mass, over V. So M over V. And density can have different units. All the units in the picture on the right are the same. They're all kilograms per meter cubed, but they could be any units of mass over any units of volume. A lot of times we say grams, if it's a liquid, we like to use grams per milliliter. Grams is a unit of mass, milliliters is a unit of volume. So for example, water has a density of 1 gram per milliliter at 25 degrees Celsius. And that means density does depend on temperature, but that means that 1 gram of water takes up 1 milliliter of volume. So if you go to a balance and you measure out 1 gram of water, it should measure out to 1 milliliter of volume in your container. Another thing that you might know or might not know is that 1 milliliter, that volume, is equal to 1 centimeter cubed, a cubic centimeter. That conversion is going to be really helpful for some different density or unit conversion problems. 1 milliliter is equal to 1 centimeter cubed. Those are the same amount, 1 and 1. And over on the right, we see that densities of gases are really low. So around 1 kilogram per meter cubed versus some solids at the bottom, those are in the thousands, like 10,000 kilograms per meter cubed. So gases, really low density, liquids in the middle, solids, the most dense. So let's practice. So we do this clicker question, and then we have 10 more minutes. So I'll give you like 1 minute for this one, and then we'll have 9 minutes left to go. So what is the mass of a 20.0 milliliter sample of titanium dioxide? And it doesn't matter that it's titanium dioxide, just matters that we know what its density is, which is 4.23 grams per milliliter. So we want to know what the mass is. And we know that density is mass over volume. So you'll have to rearrange that equation a little bit to solve for the mass. The one thing you can do is multiply both sides by volume. Then you have volume times density equals mass. And if we're trying to solve for volume, oh no, that's all we need. That's all we need to solve for mass. So density times volume. So talk to your neighbors if you want to check your answer. And I was talking through your work time, so I'll give you another 30 seconds. All right, let's get those answers in. We got 408. Let's see if we can get the last 30 or so students. 15 seconds. 5, 4, 3, 2, 1. Blast off. Oh, okay. Wrong button. There we go. And what'd we say? Okay, so almost everyone said D. Somebody pressed E by accident. Spoiler alert, I'm almost never going to have E's. But doesn't count this week, so have at it. It is C. So we want to do the density times the volume. So 20.0 milliliters times 4.23 grams over 1 milliliter. So this is going to help us next time when we do more unit conversions. Whenever you see a unit like this, grams per milliliter, know that the 4.23 stays with the grams, but per milliliter is like saying over 1 milliliter because the 1 doesn't count, right? So 4.23 over 1 is still 4.23. So we get 4.23 grams over milliliters, but there's a 1 implied there. So that 1 implied lets us cancel out our milliliters, so we just get a mass. And if we multiply those numbers, 20 by 4.23, we get 8.6 with those, and we round to 3 sig figs if it doesn't come out perfectly to 3 sig figs. Oh, you're right. I was like, that doesn't look right. Thank you. See, everybody makes mistakes. So it is D, 84.6. And if it didn't come out to that, that's what you round to because you want 3 sig figs. Because both numbers have 3 sig figs. Okay, cool. So just a little bit of an intro to what we're going to see next time. Dimensional analysis is just converting from one unit to another, basically. So it's called unit conversion. And to do that, we use what we call conversion factors. So conversion factors are fractions that express the same value in different units, 1 unit on top and 1 unit on the bottom. So that density we just used was actually a conversion factor because for titanium dioxide, for that molecule, the density 4.23 is equal to 1 milliliter. So they're the same value in different units. So another one that we could think of, I showed already today, 12 inches in 1 foot. We can say that 12 inches is equal to 1 foot. And then when we write it as a conversion factor, you can always divide something by itself. You can always divide by 1. So we can say 12 inches over 1 foot is equal to 1. As long as you do the same thing on both sides, but 1 foot divided by 1 foot is 1. So because it's 1, we can multiply anything by that conversion factor, which is allowed because multiplying by 1, we didn't change anything. So, for example, we can write another conversion factor for the metric prefix milli using mass as an example. So 1 milligram, 1 mg, is 1 times 10 to the negative third grams. You might not have memorized that yet, but that's okay. 1 milligram is 1 times 10 to the negative third grams. The 1 stays with the prefix, The power of 10 goes with the base unit grams. So this allows us to convert from milligrams to grams or from grams to milligrams, depending on what we're given. So for example, if we are given 5 grams, and we want to know how many milligrams is it, then we want to make sure that the conversion factor we use has milligrams on top, because that's what we want to get to, how many milligrams. So we're going to take our 5 grams and we're going to multiply it by our conversion factor, but we want to do it so that milligrams is on top, and that's what we end up with, and the grams are on the bottom so that we can cancel them out, because if we have grams on top and grams on the bottom, they cancel out. So 5 grams times 1 milligram, that's still 5, divided by 1 times 10 to the negative 3. When we divide by a negative exponent, when we divide by that small number, 1 times 10 to the negative 3, our number is going to get bigger. So we're going to end up with 5,000 milligrams. So that's another way to check yourself. If you're converting from a big unit to a small unit, your number is going to get bigger because more of that small unit can fit in the big unit. If you're converting from a small unit to a big unit, it's going to be the opposite. Converting from a small unit to a big unit, your number is going to get smaller. So make sure you check your answers like that. Make sure your number got bigger if you expected it to, or got smaller if you expected it to. Any questions about these conversion factors? Mm-hmm. Yeah, good question. So there are more than one way to do this. I like to do it with the power of 10 with the base unit grams, just so if you're using something like femtometers or femtograms and you don't know what that conversion is, if you always do it this way, you won't get confused. But if you do know off the top of your head that there's 1,000 milligrams in 1 gram, it is the same thing, yes. So that'd be 10 times the power of 3, but we'd move it to the top. All right, so we are going to pick up here on Friday, and we're going to look at some more difficult problems, and then we'll wrap up chapter 1 and start chapter 2. Have a good rest of your day, everybody. Thank you for staying till the end. I'll see you on Friday.